Hello again. I figured, hide my face. So I went through the first reaction. Now, this question doesn't specifically ask you about reaction 2. However, I figure you're probably going to want to know what's going on here as well. And it is different. It is one of those equations where you don't need to know the mechanism, but you need to know everything else about this. So what this ties into, and yes, I have an independent lesson at the moment, but I'm going to just take a few minutes to do this. Don't tell anyone. So essentially what happens is we're making an amino benzene, okay? And this goes back into our amine knowledge and how we make aromatic amines. And there's a few ways we can make aromatic amines, one of them of which is the reduction of a nitrobenzene. Okay, so I'm just going to talk about the reagents involved and the equation. That's all I need to know about it. It is annoying. You have to, it's like recall that you need to know, but I'll go through it with you anyway to alleviate any questions. So what's happening is we are trying to go from here, nitrobenzene, to here, aminobenzene. And so essentially what happens is, like I said, it's the reduction of this nitrobenzene. And if you remember, it's very important to note that reduction and oxidation in organic chemistry represents itself differently than inorganic. So it's not like loss of electrons, gain of electrons. In organic, we are talking about the removal of hydrogen, addition of oxygen, and how they're represented. We represent reduction with a hard bracket H. But before I go into that, I'm going to talk about the reagents and conditions. Hopefully, if my pen decides to work, it does. So number one, to make this, we throw it into a reflux apparatus with a little bit of concentrated HCl. Okay, so the reason, as always, we put anything in reflux, it's usually because the compounds involved are very volatile, meaning they have, I suppose, a low enough boiling point that they'll readily become a gas and they'll escape otherwise unless we have it in a reflux. And if it escapes, you don't get a very good yield, and companies don't want that. It's not fun. So number one, under reflux, concentrated hydrochloric acid thrown in there as well. It's just, again, to help out with the conversion here. Now, also one thing you need to remember, not only is it under reflux with concentrated hydrochloric acid, there's also a tin catalyst involved. A list spelling awful. Now, it is annoying, you don't need to know the nitty-gritties. However, it's to do with the sort of intermediate salt that tends to form. You don't need to know anything about it. This just sort of helps out with that. It's a suitable catalyst for it. Okay, so once you've done that little step, you then becomes a second step of adding sodium hydroxide. And again, that intermediate salt I talked about that you don't need to know, it just aids again with the conversion. So that's the conditions there. This is done under reflux with concentrated hydrochloric acid with a tin catalyst. We then, as a second stage, would add NaOH. Done. Now, if I was to look at the equation here, and this is probably the most important part, remember we're talking about reduction and the idea of, removing hydrogens and how we make those sort of reduction equations. So how would I do this? So I'd always, just when it comes to a benzene ring, I would always draw out the benzene ring. If you wanted to do H6H5NO3 or NO2, you can. I just like to draw out the aromatic structures because you get the same marks. So I would do NO2. It's not great. Plus, now, we are using a really, 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 really powerful reducing agent. And when we use a powerful reducing agent, we represent that with a hard bracket H, okay? What we then make very simply is our NH2, delocalized ring. And as always, we want to balance it out. Anytime we have a hard bracket H over here, we balance out with water. Now, the equation for this specifically is actually 6 H's, and I'll explain that as well. And to balance it out, then we actually have the 2 over here. This is the equation you need to know. Now, why is it 6? Why do I have 2 waters over here? What's going on? Well, remember, essentially, so number 1, on this side of the equation, I have, in red, I've got 1, 2, 6 hydrogens overall. So I've got 4 here, 2 here, that's 6 hydrogens. Okay, 6 hydrogens over here. So we balance out the 6H. Now, why is it 2H2O? Well, it's 2H2O, first of all. Not only does it balance out, but if you wanted to really look at the nitty-gritties, what's essentially happening here, the difference between these two compounds, 2 oxygens, 2 of them are dropping off, and those 2 oxygens will contribute to the 2 H2Os here. Okay, so 2 oxygens are dropping off essentially. That's why it's 2 H2O and not 1. Okay, so essentially that's it, and this independent class actually ended, perfect timing. So that's all you need to know for the reduction of nitrobenzene to make an aminobenzene. That's it. Okay, so I think I can end it here. Any questions, do ask.